All right, folks, thanks for coming. I think it's about that time, so we can get started. My name is Evan Chan. I'm very honored to be here for Philly ETE. It's my first time here. Haven't been back to Philly for like more than 20 years, so it's it's pretty awesome to see. As you'll see in my presentation, I'm a foodie. I like food, so I've already discovered Jim's cheesesteaks. But if anybody has like more hints of awesome place to try, please come up to me afterwards. So my talk is about something that we coined and call NoLambda. It's basically how do you combine a lot of things that you want to do in a modern analytics stack. You have streaming real-time processing, you have like ad hoc processing, machine learning. How do you combine that in one stack that's not too complicated? So a little bit about myself. I work for a small big data firm called TuppleJump, and those are my information if you want to find me. But basically, I've been involved in and contributed to Apache Spark and Cassandra for a long time, since the O.X days, which pretty wild old days. If anybody's just a show of hands, how many folks here use Apache Spark? And how many folks have used it before 1.0? One person. Okay, awesome. And how about Cassandra? Who's familiar with Cassandra? Pretty, a lot of folks. And who's using Cassandra in production? Few folks. Okay, cool, awesome. We'll introduce those things a little bit. So we are a big data technology leader. We provide solutions and development expertise. But we love open source. So we have a whole bunch of open source projects, especially if you use the Spark and Cassandra stack. There's some of them that are really interesting. FiloDB we'll talk about today a little bit, but we just released a connector for Kafka and Cassandra. And with some other interesting projects, such as adding a Lucene search to Cassandra that are pretty compelling as well. And what we do is that we try to take care of big data projects for enterprises. So we love to get into the source code. So basically, knowledge comes from two things. One is from deep knowledge of the source code, so we can get in and provide the most innovative and effective solutions possible, as well as that we have relationships with most of the open source communities that we're part of. So that also helps a lot. As well as a lot of experience developing, productionizing real world systems. So we'll start off talking about this big data and this new term that we call like fast data, and what it means, and talk about different architectures and how we can simplify that architecture around streaming. Right, then we'll get to look at some specific technologies. So everyone has heard about big data, but I would like to make the case to you that now it's time to talk about fast data, right? So there's a lot of data, it's really big, but it's not just static anymore, right? It's coming in all the time. This is a funny diagram, but everyone's hearing about IoT, right? There's a lot of sensors and mobile devices. They're generating a lot of data. They're coming in, and increasingly consumers are demanding that we do things with it right away, right? So this is coming in. You want to do analytics, and you kind of want to connect it with some existing systems and kind of offer services to people, such as recommendations and other things that. So this is starting to be like a feedback loop, right? This is not just static data. This is becoming like fast data, or you can call it reactive data, right? Like you want to react to it, and the sooner you react to it, the better, right? And you can think about there's different time frames for this kind of data. From a few seconds to days, and a lot of times you need to process data that integrates all these different points. For building models, for example, that might be like months or maybe even years. And there's other data like trends that are more like shorter time frames. And while we're building this out, what the management might care about is that we're building these things and that they should be up 24/7, that they can scale out automatically, carry on various kinds of complex analytics, be global in nature. So there's a lot of like these requirements, right? You want services to be coupled. So this is starting to look pretty overwhelming, right? There's a lot of pieces to this. Of course, we don't want to lose data. Who wants to lose data, right? And a lot of constraints that we need to think through. Maybe right now I just live with a very simple architecture, right? But how will it scale for future workloads? What about operations? Who's going to maintain this big stack that we throw out, right? What about costs? Like how many engineers will it take to build this? Like who can I hire to build this solution? What kind of SLAs do I need to meet? So a lot of factors to think about. And we want our systems to be self-healing. You never know when there's so I used to work in video analytics, and there will always be, it's like a lot of times things are kind of like this, but once in a while there'll be huge spikes. Like we had a couple of spikes for when, for example, like the Pope got elected or something like that, and there will be like, So how to deal with spikes in a streaming system, in a production streaming system, right? And dealing with data centers going down, this kind of thing. Of course, one good thing is that you always want to monitor everything that things fail. But so to boil this down to one theoretical use case, I want fast access to both real-time and historical data for predictive modeling for things that are coming in, and to make fast predictions. Right? It's kind of funny thing about if the supermarket was like a web interface, and you want to do this at bigger scales. So if we look at streams in general, they're not all the same, right? So we can schedule it, we can break it up into a couple of different categories. You have kind of like the sub-second or millisecond stream processing. Most people aren't dealing with those kind of timescales. Like you can think of like financial transactions or ad serving. There's very, very, very low latency. A lot of people are dealing more at, say, the seconds kind of level. And then there's other things that can be, minutes, or even when you start getting into hours, then you start talking about like, batch processing. But just to clear this up, what does the term real-time really mean, right? It just means processing events as they arrive, right? And actually, that doesn't necessarily have to do with sub-second, which is an important distinction because for some people, for certain applications, they might be, like for someone in video analytics, people were used to getting reports daily, right? To them, doing a batch processing system that gave you an hour latency was real time. So I guess just to highlight that, the requirements really has a lot of contextual meaning. Although nowadays, when people talk about real time, typically you're thinking about, there is a lot of association. Most people do consider that to be like sub-seconds or seconds, but really it just means like event-driven, right? And then there's event time, which is when the event comes in, which is when something is timestamped at the sensor. But sometimes they're not the same. Like, so usually events come in, you deal with it right away. But you can imagine, because of the network delays, something that's timestamped could actually arrive like an hour later. So you always need to deal with things like, so sometimes you'll see event processing system talk about processing time versus event time. There's also, you can think about different ways of processing streaming data. You can think of a continuous stream and kind of divide into buckets, kind of like I'm going to take 10 seconds of data here and do something with the 10 seconds data. Or you can think about it in terms of like sliding or even continuous windows, where continuous is a special case of a sliding window. The reduced by key in window is more of a Spark thing, but we'll get into that a little bit later. And you can divide stream processing into different, I guess, technology groups, or how much analysis is really needed as well, right? There's some frameworks that give you deeper stream processing. I guess you can think about Spark streaming and Flink in those terms. In particular, Spark streaming, we'll get into this a little bit, but allows you to do the machine learning on top. There's some frameworks that focus more on pure stream processing, which are a lot simpler. Most of you probably haven't heard of Gearpump. This is something from Intel for millisecond level stream processing. Zamza is something from LinkedIn that also is more for simple calculations. So let's talk about architecture. Everyone knows about the LAMP architecture, right? You have an app server, and then you have a simple database, right? And in theory, for some use cases, this could suffice, right? Maybe your data volume isn't that big, or you could like shard things very easily. So yeah, maybe this works for you. This isn't the focus of my talk, obviously, but this is a starting point. But if you want to do anything complex and shuffle data, then this is not going to scale, right? And when people realized this, they started moving to Hadoop. And what they typically do is that you have incoming data, then I start writing out to files on HDFS. And then I start running one job that will take a file and do one MapReduce stage, and that creates another set of files, and then run another job. And then people started building more and more abstractions on top of this. There was Uzi and other job schedulers that come out and kind of architect whole flow of jobs. In the end, you might write the results to a database and serve it to a web app or something like that. So this is good. It got people started with processing huge amounts of data, and everyone adopted Hadoop. And now you have Spark that can do it faster. So the pros of this is that files, everyone understands files, and it's relatively easy to understand. But the problem with these kind of jobs is that there's relatively high latency. It's not, no one would really call this a real-time architecture. And it's fairly complex to set up. Like, how many folks have set up Hadoop in production? Like, few, right? So there's a lot of components. There's just the Hadoop file system itself. You need a name node, which wasn't actually until very recently. And then on each node, you have individual servers. And then on top of that, you need Hadoop, which needs a separate set of servers on each machine. If you wanted a database like HBase, that's another set of servers. So pretty soon, you have a huge number of processes that you need to maintain. And that's not talking about Zookeeper and some of the other things that you need, right? So people started to need to deal with streaming data. So the Lambda architecture came about. And what this is an idea to take advantage of both the batch and streaming methods in an architecture. And this is what a Lambda architecture looks like. This slide is from MapR. So you have data coming in on the left. And the idea is that I'm going to fork this into two streams, or into two pipelines, sorry. So on the upper pipeline is that this data, just like the previous slide for Hadoop shows, is that it's going to arrive in files in something, say HDFS. And I'm going to do batch computations. On the lower end, I have what is called the speed layer, where I'm going to take this data and process it in a streaming manner. And the idea is that in each side, I'm going to compute views. So I have a real-time view that has really up-to-date stuff. And then I have a batch view for, say, older data. And then I'm going to serve this by combining the two views and figuring out. And the idea is to take advantage of, at a time, like the limitations of different systems. You have a batch system that is not real-time, and I have a real-time system that is not accurate. So I'm going to do a hybrid approach and blend both things. So the good thing, there's some good things about the system. Computer views can be used for a lot of different purposes, and the focus is on appending data, which you always want. But on the other hand, it's also fairly complex. So you have Hadoop itself, which is actually already a beast to set up. And on top of that, I'm adding a separate streaming pipeline. So you have a lot of moving parts. And the thing is that needing to model your data two different ways, for real-time as well as for historical and batch analysis, and then needing to reconcile and combine the two is actually it's actually not simple. If you figure out like when do I use this data versus that data, when do I transition from or stop using the real-time part and the batch part. And you start getting into a system that is very high TCO, right? It's kind of like what we call the Wild West, where you start out with one thing, but you're adding things and start, to get more and more complicated. It's actually pretty amazing, like when you start up with a monolithic app, and after a while, if you turn, your CTO, you turn around and you realize that suddenly the system looks like this. It's kind of, sometimes this happens. And it happens a lot quicker than you think, right? So here's a question, right? Are batch and streaming systems fundamentally different? Like, is there, could we think of batch as a special case of streaming? After all, what batch is I'm taking a set of, say, files, and on each node, I have a file I/O interface, right? I'm basically streaming the data record or line by line from a file. Isn't that like a form of stream processing, right? And in fact, you guys might have heard of, how many people have heard of Apache Flink? There's a few folks. So there's a new project called Apache Flink that is really interesting, and it's actually based exactly on this premise that everything is streaming. So even the batch can be built up from a streaming approach. So it's a very, very interesting project to keep an eye on. So today what we're going to talk about is what I call the NoLambda stack, or you might have also heard of this term called the SMAC stack. And what the letters stand for is Spark and Spark streaming, Mesos for orchestrating your work, Akka, Cassandra, and Kafka. It's also called my friend and coworker called it the snack stack because I like food, and if you consider the project I'll talk about, FiloDB, to include the food, we named it the snack stack. But basically, the idea is that I'm going to bring data in from sources, and this will be a primarily stream-based approach as opposed to bringing data into files. I'm going to bring data in through Kafka, which is a distributed broker, and I'm going to process it. There's different ways of processing data, and I'm going to write it to a data store and process it. So it'll be primarily, and we'll try to do everything through streaming. So let's take a look at each component and how this works. Kafka, I'm probably like everyone, who's not heard of Kafka? Wow, that's pretty amazing. Like, so this probably needs very little introduction, but Kafka is kind of like the central message broker that is used for a lot of applications nowadays. It really does operate really, really well in production. I remember running this a few years ago, and even then it was extremely simple to run. It's like the one component in your production cluster that you pretty much don't have to touch. Unless you're reconfiguring or restarting it. So it really is very fantastic. And it is a persistent data store, which is another really good thing because you can recover your data. They are coming out with a new thing called Kafka Streams in version OLAP-10. So this is a library that you can deploy in your application and it basically gives you stream processing primitives. Of course, there's a lot of alternatives for doing this, but this allows you to do. Let me see. Well, we'll have examples for this later, but it allows you to use a really nice DSL to do common streaming operations, but it's not distributed. There is Spark streaming, which most of you have probably heard about, but just to recap, it basically divides your streams into what are called micro batches. So it would take, say, 2 seconds of your stream, and that would create a batch. Then it can run all the standard Spark operations, which are a lot. You can do machine learning on it, you can do graph processing, you can do SQL. They're coming up with a streaming DataFrame thing in 2.0, which is streaming SQL. The great thing is that you can use the same algorithms that you would in your batch processing in your stream processing, which just makes it very powerful. Cassandra, I'll go into this a little bit more details, and not everyone is familiar with it, but Cassandra is a horizontally scalable NoSQL database. The really good thing about it is that the operational model is very simple. Every node, Cassandra node is exactly the same because it's a peer-to-peer system. So I have 10 nodes, I start up Cassandra on all of them, they talk to each other, and that's pretty much it. I mean, that's not it, but in terms of like setting up, that's it. So it's very easy to get started. And it is known for having phenomenal write bandwidth. And as well as it's very flexible data modeling, like now that you can do lists and sets and things. However, it is really designed for a very simple data model, like in terms of queries. You model your data so that by how you want to query it. And so it's more transaction-oriented, really, than analytics-oriented. How many folks have heard of Akka? Probably. Actually, that's more than I would have thought. That's pretty awesome. Or how many people have heard of the actor model? Right. So Akka is the actor model or Erlang for the JVM. Right. For those of you that are not familiar, it's the idea that instead of the traditional way that you make things concurrent is that I'm going to put some blob of data in memory and I'm going to share it among several threads. Right. So that's good, but then that doesn't distribute. And sharing data in a scalable way and a fault-tolerant way and without running into a lot of bugs is actually fairly hard. So what Akka says instead is, I'm going to be like one actor, I'm going to be another actor, and the way that we talk is instead of sharing data, we're going to pass messages back and forth. And these messages are immutable, and it turns out if you build the application this way, you can automatically build an application that can distribute very easily. So yeah, I'm a big fan of Akka. It's pretty awesome stuff. And you can use it to build very low latency frameworks. Here's an example of Kafka streams in Java. It's just to show you what it looks like because it's a fairly new feature that I can basically take a stream of, say, words, and I can, in a few lines, I can easily split it and to create a word count very easily. But again, this is a library, so this is something that you would include in your app and deploy it, which means that it's also not distributed. Here's an example of taking a stream of data, saving the raw data, and then computing aggregates. And what you can do is that I can take, again, the stream is discretized into RDDs. If you're not familiar with, basically that's like a unit of distributed data in Spark. So I can take that, save it to a data source. We'll talk about FiloDB in a little bit later, but basically I can save this to data source raw events. And then I can also create aggregates and save them to Cassandra for reading for, say, a dashboard. And this is an example of using Akka together with Cassandra to return a query. This is based on a weather dataset example. And what happens is that when an actor receives a message to get data, it's going to run this high-low method that does a query. The Cassandra table and the where clause will actually end up executing a Spark query to the underlying Cassandra table. And then it will collect the data asynchronously and do some processing on it in the map method and return objects, monthly temperature, to another actor that could, say, serve up the request. And finally, this is an example of integrating the stack and with the machine learning library. What we're doing here is that, let's say that you have a training stream of data, and we're going to feed that through a linear regression. And once we've built up the model, we can then use that to run predictions on the new stream of data that's coming in. So what are we missing here in this whole pipeline? So we have in Kafka a way to ingest and distribute messages, publish, subscribe. In Spark and Spark Streaming, you have a way to process the data in a streaming manner. That's really good. In Cassandra, we have a data store. We could then, let's say Spark SQL, but just think of using Spark to further process the data out. So in theory, we have all the components that would allow us to do both streaming and batch analytics. So we're at a pretty good point right now. However, when you use Cassandra for storing and processing huge amounts of data, you run into some bumps. So when you need to process huge amounts of data, not just your minutes and hours, but let's say that you want to do months, right, or years of processing, then the storage efficiency, like how compactly you can store things, and the cost of storage, as well as how efficiently I can query huge amounts of data, becomes very important. And actually, this is one of the things that has always attracted people to Hadoop, because storing them in files is relatively efficient for reading, right? Unfortunately, regular Cassandra tables are not very efficient in terms of storing large amounts of data. So what we need to do is think outside of the box a little bit. And for those of you that know Cassandra very well, it's really been up to you how you store your data. And recently, Cassandra has added a lot of really goodies, like I can store arbitrary arbitrary objects, nested things, and I can store lists and sets. But in the beginning, it didn't have that. And so those of us from the early days were able to, but that also forced those of us in the early days to kind of think outside the box a little bit and store things and kind of think about how to do things very efficiently. So this is the quote from Proverbs, that all hard work leads to profit, but mere talk leads to poverty. So for a while, I've been giving like the architecture talks. And so people were like, maybe we should do something about it. So this led to the creation of an open source project called FiloDB. And what FiloDB is, it's a distributed versioned columnar analytics database that is built for modern streaming applications. And you can find it at github.com/jump FiloDB. What this is first you can think of it as fast analytic storage. So it stores things in Cassandra, but it gives you scan speeds that are competitive with the best file formats in Hadoop, namely Parquet. So you can scan data at the same speeds, but you get, unlike files, where basically if you store things in files, you have to think about how to organize things by file name and figure out which files to read out, and that's basically your filtering mechanism. What FiloDB gives you is the scan speed of something like Parquet with the filtering that you would get with a real database. You can define partition keys that are very fine-grained and read data like only for a specific, say, user ID or something like that. And the efficient columnar storage that it's based on gives you much more efficient storage than native Cassandra tables. One way you can think about the landscape, like NoSQL, actually I should have compared this for other NoSQL database, but I didn't really have time. For analytics, like I said, there are two variables you really care about in terms of query speed and the storage costs. So basically you want things that are on the upper right corner of the table that are both have efficient storage and can query quickly. And you can see Parquet is kind of like, in that corner. If you just use regular Cassandra tables, it's kind of on the other end of this table. But there are things that you can do that we've known. There's various ways of storing data that are a lot more compact. Like if you use thrift, traditionally what you did if you wanted really good performance was that you would store your records as thrift blobs. And that would get you much further to the right in terms of storage efficiency. There are things like you can cache your data in memory, but that's not desirable from a couple standpoints. Or you can use something like FiloDB that stores it efficiently on disk. That way you can read it out quickly and get high storage costs. There's a blog with a lot of details that I detailed about different options in Cassandra that you can read. And because it's based on storing data in Cassandra, you get all of the benefits of Cassandra operations, which is again that you don't have any single point of failure because it's a peer-to-peer system. I can replicate my data across. This is actually pretty cool if you don't know. Cassandra can automatically replicate your data across data centers. And this is exactly designed for the scenario where one AWS availability zone will fail, right? Which we know happens. And so you can spread out your data in Cassandra amongst several availability zones or several data centers, and it will replicate and it will survive data center outages. FiloDB has a Cassandra-like data model. Basically, I'll go into this a little bit for those that are not familiar with Cassandra, which might be a lot of you. There's something called a partition key, which is the way that you distribute data. So if I have a partition key Bob and another partition key Christopher, right? Then basically what Cassandra is going to do is it's going to hash those partition keys and they will end up going to different nodes. So this standard way of, it serves two functions. One is to distribute data, and another way is that you can control exactly everything that is in a partition key is guaranteed to be on a single node. So you know that if I model my data such that my data fits, most of my queries fits on one partition, I can get it very quickly using one thread on one node, right? FiloDB, in addition, adds something called a segment key, which is that because it's a column store that stores efficient binary blobs, we need a way of grouping records or rows into blobs. So that's what a segment gives you. And but the main takeaway is that, like Cassandra, FiloDB is a primary key based model. So that if you ingest things using the same primary key, it's going to be stored once, not twice. So you don't have to worry about, in HDFS typically, if you have a fail-safe system, you could get data twice and you might need to duplicate it. And it is designed for streaming, being that writes are idempotent, but at the same time, while they are idempotent, it keeps your data sorted. You can use SQL for querying and ingesting. One thing that I've learned is that I know there's a big term about NoSQL, right? But if you go into real-world enterprises, that SQL is still a really big deal. And there's a lot of people heavily invested in SQL that you can't really get away from. So you can think of FiloDB as kind of like a SQL on top of Cassandra in many ways, except that it's for analytics and not so much OLTP. As I said that I like food, so it's named after phyllo dough, which is the ingredient used in virtually every great dessert. And what it really conceptually stands for is like you can think of layering data in versions to your data. So where does that leave us? So this gives us a stack, what we call NoLambda or snack stack, that gives you the ability to process real-time data ad hoc, but allows you to do ad hoc and ML and deep analytics all at the same time. For example, you could use them for different use cases. You can use regular Cassandra tables for things that are super pre-aggregated and you need like millisecond access for dashboards, right? But you can use FiloDB for storing a lot of event data that you can use to build models. Well, here's a diagram that explains that a little bit better. So basically, I have events coming in through Kafka, you process it in Spark streaming, and you can store it. You can kind of have a pipeline that stores it two ways, one for short-term storage in regular Cassandra tables, and in FiloDB for longer-term storage where you need to read a lot of data for building up, say, models. And so one startup is using this way, to store data for building real-time predictive models. They're using it for marketing data. And they're choosing to use this stack over something like Amazon Redshift, because Redshift gets a lot more expensive when you have a lot of data. And another enterprise I'm working with, which is one of the largest fleet management companies in the US, is basically moving the data warehouse from a traditional data warehouse to this stack. So the use cases, you can probably glean from what I talked about, let's say data warehousing where I need to run reports at the end of the month, and it's not cost effective for me to transition away from traditional reports and a traditional star schema, or maybe sometimes you can't because maybe your attributes are being updated, right? So if you denormalize your data, you might end up having extremely complicated ETL where you have to update existing tables in very complicated ways, right? Another use case is time series and IoT type stuff. And another use case is for doing kind of in-memory app server. I won't go into that in a second, but if you're interested in that, you can talk to me. It is, even though most people think of Spark as a faster Hadoop, it actually is possible to use Spark for doing as a web server. Here's a real-world data warehouse architecture stack. This is something that is being productionized as we speak. Is that at the bottom I have Cassandra, and above that, basically, I have a Spark Hive context, which uses two connectors. One is the regular Cassandra Spark connector, and another is the FiloDB connector. And that's where it sits, is that right now FiloDB is a jar that you deploy, so it doesn't involve deploying another component in the stack. And basically, the BI applications would connect to Spark through the Hive Thrift server, which provides a JDBC interface. You can also use ODBC, so it can connect to virtually all of the standard BI tools out there, Tableau, Microsoft reporting services, or whatever. Oops. I'll just go into this really quickly because this is probably obvious from previous content, but if I compare it to HDFS and Parquet, the key difference is that you have a database like API instead of files. I personally find that files are a lot harder to work with, although they are very efficient as a developer. And I get filtering, I get more fine-grained filtering. How many people have heard of Druid? Yeah, a few folks. Maybe I won't go into this too much, but Druid is a very interesting OLAP database that stores summaries in memory and can give you very fast answers. But basically, you can think of FiloDB as a way to store raw data and do just about anything that you could want with it. Here's a really interesting example, which I'm going to go into a demo really soon. It is the New York City taxi dataset. How many people have heard of this dataset? It's really, really interesting. I used to work in open data. Basically, someone foiled the New York City to release the taxi records. And so what you see is that you see a record of every single taxi trip that people have taken. Don't worry, it's all anonymized. But basically, for every taxi ride, you have the number of passengers, pickup points, drop-off points, and information like that. And let's say that I want to do some interesting analysis on it. So depending on what kind of analysis I want, but let's say that I want to analyze individual taxi rides as well as aggregates. So what I would do is I would store in the partition key a hash of the medallion, which the medallion is basically the cab ID. And in this case, I'm using a function built into FiloDB called string prefix. Basically, I'm taking the first 2 characters of the medallion, which hashes my data into about 600, well, 300, yeah, 300 to 600 partitions. So I'm distributing that, and for any single taxi, I can look that up from a single node very quickly. For a segment key, what I'm doing is, this is a standard time series technique. So I'm basically grouping 6 days worth of taxi events, which by some calculations is enough to give like a good, a large enough segment. And the row key is basically part of the primary key. It's this way of disambiguating individual taxi events. And I'm going to switch really quickly into a demo, which hopefully you guys will enjoy. But so what I'm using here is called a Spark Notebook. Some of you might have heard of this. It's a pretty cool way of visualizing and interacting with your data. And I can get out, I can show you what the records look like if we just run this. And you can see that for each taxi record I have, the trip distance, kind of like the drop off and pick up longitude, this kind of thing. But what's really interesting is what you can do with the data. So let's say that I want to pick up, I want to visualize pickup points for one driver. So you can see that this is a standard SQL query. Basically, I'm selecting out the pickup latitude, longitude, and the passenger count. And let's say that I'm going to display it on a graph. And here I can see basically what I'm doing is I've visualized for one taxi driver all the different pickup points for a month. And the radius of the circle is the number of passengers that are picked up. So most of the time it is just one passenger, but sometimes you can see there are multiple passengers. But the really neat thing is that I can interactively select a different taxi, and you can see that this returns results almost pretty much instantaneously, right? Which is pretty cool. And you can say that this is cool, but there's not that much data for a single driver, so let's do something more complex, right? Let's say that I want to analyze passengers by the time of day. And see how the pattern changes depending on what time of the day it is in New York. So let me see where we are. Okay, so here we are. So this is just to show you that there's a lot of data. This is, by the way, this is 15 million rows in this data set for 1 month. And this is all like running out of my laptop. So it is not running out of a cluster somewhere. For a single hour day, I have like 650,000 records, which is still quite a lot of data. So what I'm going to do is I'm going to compute the average trip distance and the average speed of the taxi ride based on the trip distance and the trip time. And I'm going to do that for all hours of the day. So this is basically a whole table scan running over all 15 million rows. And we're going to do this interactively. And you can see this comes back as I'm talking. In a couple seconds. And now I can get for every hour of the day the trip time and speed. So you can do like really fast analysis with this. And then I can plot it. Interesting. So this is kind of like what you would expect, what you might expect, but it's still pretty interesting that the highest taxi speeds are at 5 and 6 a.m. There's nothing going on. It's a little bit lower for 1 to 3 a.m. There's still people like partying, and you can see like during the middle of the day, during the rush hour and the middle of the day, it's pretty much like all like pretty low. The average is like below 15 miles an hour. Kind of gets up as you get into the night. And finally, this is something really cool. But what I'm going to do is I'm going to do a heat map. So let's say that I want to find out on a map the variation between density, like how many rides I get at that point, as well as the speed, right? So in one map, I can see like the two variables plotted. So what I'm doing here is I'm going to do a SQL query, and this is something you can do in Spark. This is a fairly non-trivial query where I'm doing a group by geographical location. I'm doing basically a binning, and I'm summarizing the speed and other variables. And then I can take that, and this is in Scala, but you can do the same thing in Java. I can take this and do some custom classification on it to say if the speed is below 15, I'm going to plot with red. And if it's above 20, I'm going to plot it using green. And this is what it looks like. So I'm going to do a map. Hold on for a minute. Okay, we might need to come back to this. Because sometimes, as we said, like demos invariably, don't quite work. So let me restart this. Restart, reload this page, and we will load the data. And we will scroll down and load some more data and rerun this. So, okay. All right. Okay, so this is, oops. So this is what it looks like. Basically, what I see here are circles where the radius is the number of this density, the number of rides at that point. You can see the outlying areas. There's very few rides. Most of the rides are in Manhattan, but there's some exceptions. Like this is LaGuardia, I think, and this is JFK. And the color is the speed. And what I'm going to do is I'm going to have a widget where I can slide the hour of the day back and forth. Okay, and as I'm doing this, this is going to interactively run this fairly complex query and plot it on the map in real time. So this is unfortunately a little bit hard to see because of the size of the screen, but as I slide this back and forth, you can see that this actually updates in real time for like that 650,000 records, which is really darn cool, right? And so you can see at 6 a.m. things are mostly green. When I slide this to rush hour, this will become red. As I slide it further during the day, it will change. So this is pretty awesome like processing. And if you know anything about geographical processing, you know that traditionally what is done is that maps, you have to compute tiles because there's so much data and you can't display in real time. What people do is that they compute graphical tiles and for every single slice of data you could possibly imagine. But when you have technology like this, you can process in real time, which means that I can do virtually any kind of filtering I want in real time, as well as update this for real-time data. I don't need the latency of generating tiles, right? So this is, if you're in a map business, this is very, very exciting. Yep. And just a quick thing about machine learning. We don't really want to build static models because static models don't really change. And taxi drivers, as we know, is that's a dynamic population, right? And so we don't want to do that. We want to continuously rebuild our models based on the latest data, right? So this is just a slight variation of the code before, but basically what I can do is I can write my raw stream into FiloDB, but I can also push that into the linear regression or whatever algorithm we want to use. And I can update my models periodically or even continuously and use that on new data. And this is basically what it looks like, is that the raw data goes into FiloDB. I read it out of Spark. I build the model periodically. And what I call learned data, there might be a better term for this, but basically you can take new data that's coming in, run it through the model, and do your classification, do your predictions, and it comes out in real time. And the advantage of FiloDB for this is that because I can read a lot of data, but I can also update data in FiloDB, then it can enable this kind of continuous reactive machine learning. And that's about all I have. We're productionizing it right now. There's a lot of interesting things in roadmap. If you want to contact me, there's my email and my Twitter handle. Thank you very much. Yeah. So, hold on.
Yeah, a couple of questions. Did you look at real-time indexing databases like Solr or Elasticsearch kind of databases and compare with your FiloDB?
Yeah, so I think the question is, have I compared against, like, say, Elasticsearch?
Elasticsearch or Solr?
Yeah, I think the Solr, so it's a kind of different purpose. I would say that FiloDB is more for analytics, kind of like they say you're building models or you're running like SQL queries, and it's not so much for targeted search. You can use it. You can use FiloDB together with Solr on Cassandra. You can use it side by side. So I can build Solr indexes, and then I can do real-time searches, and you can do analytics using that. So I would say the two are like more complementary rather than, I would say there are different use cases.
I mean, Solr and Elasticsearch also offers a limited amount of analytics as well, using dashboards like Kibana and all the extract standard. Yeah, yes. So they do some analytics as well, but not deep machine learning kind of things. Maybe. Yeah.
There's some similar. Like for certain things, you can set up indexes in Elasticsearch and get that data out right away. So I would say, like, for example, the difference is for certain dashboards, like for the front page of a dashboard, like running query against say Elasticsearch or against Cassandra pre-aggregates is very easy, right? But let's say that you want to enable like very deep kind of slicing and dicing, for those scenarios, then you would need something more flexible.
Right. Another question is, you touched up on the Apache Flink.
Yes.
Did you ever experimented with that?
No, I haven't. That's why I didn't really talk about it. I haven't spent any time with Flink at all, but I would love to. I think that's definitely going to be a very interesting technology.
Yeah, that's basically what taking the NoLambda architecture to next level with what called Kappa architecture, which is
so this is very similar to the Kappa architecture.
Right. So you didn't put the name right.
For all these things, basically.
So Flink is taking next level essentially, considering everything as a stream, so underneath.
Yeah. I thought it would give a break from the Greek letters, just something a little different. Thanks. Cool. Well, I'm available for questions afterwards, so yeah.